Hello, I'm Cameron, and I'm here with Victor to expand upon our alternative violin bow design. So let's jump right in. To get an estimate on the physical qualities of the bow, a finite element analysis was conducted on the bow stick without any hair. Due to lack of access to a beginner-level violin bow, all of the measurements taken are estimates from multiple different sources. The material properties applied to the model were assigned to be as close to Pernambuco wood as possible. A static and modal analysis was conducted in ANSYS Workbench. One end of the bow, near the frog, was fixed to imitate where a human hand would grip the bow. A force of 2 newtons was applied to the frog and the head of the bow to imitate where the hair would put tension on the stick when force was applied. The first 2 mode shapes of the modal analysis are presented here. The modal analysis resulted in 12 modes with a frequency range between 73 and 1300 Hz. The simulated bow experienced a max deformation between 10.36 and 10.906 millimeters, usually located in the middle of the bow. At the points of low stress, located closer to the head and the frog, the deformation was typically in the range of 2 to 4 millimeters. The finite element analysis of the bow was conducted to have an understanding of the bow stick under normal conditions and to act as a control to compare the analysis of the bow and the hair. Although multiple analyses should be run to ensure the accuracy of the results presented, due to time constraints, it was only possible to conduct one analysis. A prototype model of the band of hair and how it clips into the bow was also carried out in SOLIDWORKS. The intention was to create a band that simplified the repairing process on the bow so that a beginner could do it themselves instead of taking it to a professional. The design requires the bow and the strap of hair to be completely refigured in order to allow for the simple installation while also being inexpensive. Pictured on the left is the portion of the band that clips into the head of the bow. This part will slide directly into a track on the bow head. On the right is the redesigned bow head that has a track for the strap head to fall into place. Ideally, there will be a small mechanical spring latch that the strap head can slide over. Once the latch falls into the pit in the middle of the strap head, the latch prevents the strap head from moving. The aim of the track and the latch at the head of the bow is to allow for tension to be created in the hair as it is being pulled further and further away from the frog, where the other end of the strap is firmly clipped into place. Here shows the redesigned frog on the left. We have small protruding studs that allow for the band to easily be pressed into and interlock with the frog, similar to that of Legos. On the right is the end of the strap of hair that can be latched onto the frog.
In order to experimentally test the sound production of different materials, a simplified rig had to be made. This was not done to the specifications above in order to save time. First, a violin bow was stripped of its hair and the frog was removed. Strips of various materials were affixed to the bow. This bow had a frog which was attached to the hair via a screw. Materials were then attached to the frog by creating a hole at one end and then screwing it down. Once removing the hair, a wooden surface was available at the tip of the bow. A wood screw and a washer were then used to attach the materials at this end. Aside from the control of standard horsehair, 3 materials were tested. These materials were selected based on their availability and the performance of similar small strips. The materials were the glossy and rough side of poster board paper, polyester ribbon, and nylon strap. For paper, 2 strips were used layered on top of one another as a single strip was tested but broke while trying to achieve the required tension. All recordings are of a down bow on an open E. It should be noted that the in-person sound of hair was noticeably better than the in-person sound of any other material. Personally, this difference is not as drastic in the recordings as it was in person. The recordings being analyzed are of a down bow and then an up bow on an open E, A, D, and then G. While it is clear that the amplitude spectrum performs best for materials with rosin, the difference between the rosin materials is not as drastic. The best performances appear to come from standard horsehair on both sides of the paper. Comparing the 2 sides of paper, the glossy side does seem to have a slightly better spread of peaks. This agrees with what was heard while testing. Although there are many types of materials that can try to imitate horsehair still sounds better. However, while the rosin is still required, some smooth surfaces can get quite close to matching the existing sound, while very bright, glossy paper works surprisingly well. Further analysis using microscopic imaging, friction tests, and rosin adhesion tests should be performed in order to isolate the variables which actually have an impact on the sound. Re-recording with superior sound equipment would also be beneficial.